the definition of Fermi energy level in semiconductors. In metals, we define that if you take the energy levels, they will be filled from the lowest energy level, and at 0K up to certain levels, electrons are filled. And this highest occupied energy level, we call it as the Fermi energy level in metals. But in metals being conductors, there is no separation between conduction band and valence band. They are superposed. Therefore, the highest energy level can be identified. But in case of semiconductors or insulators, we have seen that there is a energy gap between conduction band and the valence band. So this gap between the conduction band and valence band is small in semiconductors and approximately equal to 1 electron volt. Then therefore, if I draw the energy band diagram of a semiconductor, if this is the energy, and we have seen that this is the valence band VB, and the conduction band will be above this with a small energy gap. Therefore, this is the conduction band if I take it. So there is a gap between this. Then how do I define Fermi energy level? Is it the highest energy level in valence band, or is it the highest field energy level in the conduction band? So to determine the definition of energy level in semiconductors, I cannot take individually the highest occupied level of valence band or highest occupied level of conduction band. Therefore, the definition will be something like this. I first take the a conduction band and a valence band, of course. So I draw here, this is suppose a conduction band, and I suppose here this is the valence band. And you know that there are lot number of energy levels which are closely spaced in conduction band as well as in valence band. And this is the bottom edge of the conduction band, which we call it as EC, and this is called this is a top edge of the valence band EV. So electrons will be there for an energy level greater than or equal to EC, and holes will be there for the energy levels below EV or equal to EV. So we have holes here and we have electrons here. So they may be there in different energy levels because they are slightly different energy levels are there in a band. Then to define Fermi energy level, you calculate the average energy level of holes and average energy of electrons and take the weighted average of these two. What do you mean by weighted average? Weighted average means that suppose say there are some numbers like 1, 3, 5, 4, okay, and suppose say if I want to take average, I will add them and divide by the number of quantities in it. If I have suppose say 2 also there, 3 is also there, and 5 is also there, then in this series to find the average of this, the process is same. You add all of them, divide by the number of quantities. But in this case, I say that 3 is repeated twice. Therefore, weight of 3 is 2. Therefore, weightage is 2 into 3. I can write. Similarly, suppose say 5 is repeated 3 times. Then weightage of this is 3 into 5. Plus add them. While adding, you have to count the total number 1, 2, 3, like that. So that is called as weighted average because the hole is in this with this energy level, and if I take an electron somewhere here, the electron is in this level. In two electrons are in the same level, maybe up some spin and down spin. Therefore, 2 into this energy level. Likewise, I take the weighted average of all the electrons in the conduction band and all the holes in the valence band, and that will be the average weighted average of the energy levels in conduction band and valence band, which are filled by holes and electrons. And that weighted average will not be in conduction band or it will not be in valence band. It may be somewhere in the energy gap. So, but we know that in energy gap, energy levels does not exist. But the Fermi level is a reference level, may not be there, but that energy level will be taken as a reference energy level. Therefore, in semiconductors, the Fermi energy level, we define it as something like this. This is the valence band. This is the top of the valence band, means no holes will be there above this EV, and holes are there in it. And I take a conduction band. This is the bottom of the conduction band, where below EC there are no electrons, but above EC electrons will be there. And we have some electrons in it. I have taken some electrons. Now to define the Fermi energy level in this, in intrinsic semiconductor, the number of holes and the number of electrons are same because they are formed due to breakage of covalent bonds. Each covalent bond breakage will give you one hole and one electron. So therefore, for every hole, we have an electron here. Hence, in intrinsic semiconductor, number of electrons in conduction band are equal to number of holes in valence band. So thereby, we say that the weighted average of these carriers in conduction band and valence band is exactly at the center of the EG. This is the EG. So Fermi energy level is neither in CB nor in VB. It is this at the center of the EG, that is forbidden energy gap. So in intrinsic semiconductors, Fermi energy level is called EFI. E, either F is Fermi energy level, and I, the suffix, is for intrinsic semiconductors. So we call it as EFI is the Fermi energy level, which is exactly at the half of the forbidden energy gap, provided that mass of effective mass of electron is equal to effective mass of hole. If the effective masses are different, then Fermi energy level need not be at the center even for intrinsic semiconductors. Okay, so therefore our definition is, in semiconductor, weighted average energy levels of holes in valence band and free electrons in conduction band is called Fermi energy level. So in intrinsic semiconductor, we have seen that number of holes is equal to number of electrons. Therefore, the Fermi energy level EFI, I write it as, to see that it is the Fermi energy level for intrinsic semiconductor, which is a reference level for the semiconductors. So EFI is the Fermi energy level. So there is a difference between the slight difference, but Fermi energy level is Fermi energy level anywhere, whether it is a metal or a semiconductor, but the definition is slightly modified. Now we will look at Fermi energy level in N-type semiconductor, because we have already seen that Fermi energy level in an intrinsic semiconductor is at the center of the forbidden energy gap. Now in N-type semiconductor, we know that we add pentavalent atoms, therefore there will be more number of electrons than holes. Therefore, the number of holes in valence band I am showing here as few, maybe 1, 2, 3, 4, 5 are there. But electrons in the conduction band are more because of addition of pentavalent atoms and also because of breakage of bonds. So therefore, I have more electrons than holes. Therefore, I'll call electrons as majority charge carriers in N-type material. Now, when I add pentavalent atoms are ready to donate one electron. If they are donating one electron, that electron will exist as a free electron, and that should be in conduction band. Therefore, if I add impurity atoms, pentavalent impurity atoms or donor impurity atoms, they are donating electrons. So these electrons should go into the conduction band. If they want to go into conduction band, the donor atoms or impurity atoms should have their own energy levels, in addition to the conduction band and valence band of semiconducting materials. So therefore, added impurities will also have their energy levels. those energy levels of impurities are added atoms as defects. Their energy levels in n-type, they are called as donor energy levels. If donor energy levels are close to conduction band, then it is easy for the electrons to go into conduction band. Hence, we have chosen pentavalent atoms as donor impurities, and therefore the donor impurity levels are very close to conduction band. Donor impurity levels also I have shown as a band of energy levels, and they contain now free electrons or excess electrons. Therefore, these are the excess electrons, few electrons are there in the donor energy levels, which are very, very close to the bottom of the conduction band. Thereby, at room temperature or slightly higher values, these electrons will go into it. But remember that these are free electrons. When they are going to conduction band with a small energy that is supplied by room temperature, they don't leave any hole in the donor energy levels because they are free electrons. They are jumping only. They are not bound electrons, and they are not because of breakage of bonds. If there is a breakage of bond, then there will be a hole created, but it is not that. The donor impurity which we have taken has 5 electrons as a pentavalent one. 1, 2, 3, 4 will be there. This 4 is forming bonds, but it is giving one extra electron. This is a free electron. If it goes, it will not give any hole. Therefore, the electrons supplied by the pentavalent atoms with donor energy levels, they are close to the bottom of the conduction band. Thereby, we call now here the donor energy levels. In addition to the bottom of the conduction band EC, this is the bottom of the conduction band, this is the top edge of the valence band, and we have donor energy levels called as ED. This is also a very important energy level that depends on what type of impurity atoms of pentavalency you are adding into the material, and that energy levels are EDs. And if I now take it, I have to define the Fermi energy level as a weighted energy level. Defining it as a weighted energy level, here now the weightage of electrons are more compared to holes, because donor impurities will increase only the electrons in the conduction band but not holes in the valence band. Thereby, the number of electrons are more in the conduction band, hence weighted average will shift towards the bottom of the conduction band. Therefore, in n-type semiconductors, the Fermi energy level is not at the center as in the case of an intrinsic semiconductor, but the Fermi level will shift towards the bottom of the conduction band. And this is because there are more number of electrons in the conduction band, thereby the number of electrons are more, weighted average is more for electrons, hence it is shifting into this. And actually this is the position if it is an intrinsic semiconductor, that's why I'm writing it as EFI. And this I'll write EFN. Okay, EF is the Fermi level and EFI is the Fermi level of intrinsic semiconductor. EFN is the Fermi level of n-type semiconductor, which is now close to conduction band. It is not at the center of it. Okay, this is about Fermi energy level in n-type semiconductors. And go to p-type semiconductors. When I go to p-type semiconductors, we know that holes are majority charge carriers in p-type semiconductor. Therefore, the number of electrons in conduction band are less, and they are only few, and I have more number of holes as a majority charge carriers in the conduction band. These holes are created because of addition of trivalent impurities. If I add a trivalent impurities, I have only 1, 2, 3 electrons. This is empty one. Therefore, addition will only create the holes but not electrons. And therefore, whenever I add trivalent impurities, they are in requirement of an electron to complete this hole. Therefore, they are called as acceptor impurities. And these acceptor impurities material atoms which we are adding into semiconducting material will have their energy levels called acceptor energy levels. And acceptor energy levels are the energy levels that are that belongs to the impurity atoms that are added to make p-type semiconductor, which are trivalent atoms. Therefore, I will show here the acceptor energy levels. And these acceptor energy levels, I represent it by EA, where EA is acceptor energy levels. ED is donor energy levels in n-type. Okay. Now, as there are more number of holes are there, these holes will come down, okay, here, and therefore the number of holes in the valence band will increase, and once the holes are coming near, and there will be more number of holes in the valence band, and acceptor energy levels are very near to the top edge of the valence band. Therefore, there are more number of holes in the valence band than the electrons in the conduction band. Hence, weighted average level shifts towards the bottom edge of the conduction band, valence band. So, therefore, EFP is called Fermi energy level in p-type material, which is close to the top edge of this one. So therefore, this is the intrinsic Fermi level. Hence, we have energy levels in n-type or p-type. One is EF, that is Fermi energy level, EFI, Fermi energy level in intrinsic semiconductor, and we have EF, AN, Fermi energy level in n-type material, EFP, Fermi energy level in p-type material, and ED, donor energy levels in n-type, and this is because of pentavalent atoms, and we have EA, acceptor energy levels due to the trivalent impurities in p-type. Hence, therefore, in short, in intrinsic semiconductor, Fermi level is almost at the center of the Fermi energy gap. In n-type materials, Fermi energy level is close to the conduction band, and in p-type materials, Fermi energy level is close to the valence band. But now, is it constant always, Fermi energy level? Is it exactly lies always at the center, or only close to the conduction band, or close to the valence band? No, the Fermi energy level is dependent on various factors like the effective mass. Okay, if I take EF will be dependent on various factors. The Fermi energy level is not constant. It depends on the effective mass, m star of electrons, or me star is the electron effective mass, mh star is the effective mass of holes. And it also depends on the temperature at which we are operating the device, temperature, both in intrinsic and extrinsic, and it also depends on the number of charge carriers N and P by doping. If you dope more number, then the Fermi level also changes. Hence, we now look at how the Fermi energy level will change with temperature. So the variation is we'll see in both the intrinsic semiconductors and also extrinsic semiconductors. So now look at this n-type semiconductor first. So this is the energy band diagram I'm taking. So this is now in addition to the distance d on this, okay, I'm also taking temperature T. So if I am changing the temperature from 0K to several values, how the Fermi energy level changes, we have to look at this. So this is the valence band, this is the conduction band. We have more number of electrons because it is an n-type material, and this is the bottom edge of the conduction band, and this is the top edge of the valence band. Now I'll take the donor energy levels, which we generally represent it by ED, is the donor energy levels. And there are donor energy electrons, they will go to conduction band. Now, this is the case of Fermi energy level at room temperature or maybe 0 temperature. Now, as I'm increasing the temperature, I have to see how do I get the Fermi energy level. The Fermi energy level which I have shown here is intrinsic Fermi energy level EF. This is the Fermi energy level when it is a semiconductor. This diagram we have already seen in the earlier slide. Now I'll change the temperature and I see how it is changing. So I am now taking at two different temperatures and I'm changing the temperature from lowest value to highest value in this. But here I have chosen two temperatures called a TD and a TI, where TD is called depletion temperature. We call it as depletion temperature. And I call the TI as intrinsic temperature. So this is intrinsic temperature. So these two temperatures are important where the Fermi energy level changes, okay, from their position. So initially I suppose temperature is 0. When T is equal to very low or maybe approximately equal to 0, if I take it like this, then the EFN Fermi energy level in the n-type material will be at EC. Okay, EC is the bottom of the conduction band plus ED. ED is the donor energy level by 2. That means initially when T is equal to 0 approximately, EFN will be, this is EC value and this is ED value. Okay, so this is the ED value. It starts at the center of this almost, and as temperature increases, it decreases and comes like this. When T is equal to a certain temperature called as depletion temperature, this depletion temperature means that as the temperature increasing, available energy of thermal energy increases, therefore most of the electrons will jump into the conduction band. At certain temperature, as it is increasing, all of the electrons provided by donor atoms will go into conduction band and the donor levels become empty. So that is, the donor levels are depleted from charge carriers. As the charge carriers has gone that side, okay, donor impurity levels are less. Thereby, as the temperature is increased, breakage of bonds also will take, and hence hole formation also starts. Thereby, Fermi energy level falls down as the holes are also increasing. At a TD, okay, exactly the Fermi energy level will become equal to EFN. If I still increase the temperature, then okay, at the number of holes increases and therefore Fermi energy falls and approaches intrinsic character. And if T is equal to TD, then at that temperature the Fermi energy level EFN, okay, EF is now is equal to and coincide with the EFN. Okay, this is the EF at T is equal to 0, and this is the EF and is equal to EFN at TD. Exactly, it comes here. As the temperature is further increased, when the temperature is equal to Ti, called intrinsic temperature, means that most of the, as the temperature is increasing, the number of breakage also increases and thereby holes also increases. As the holes are increasing, they acquire intrinsic character, thereby number of holes almost equals to the number of electrons. Therefore, the Fermi energy level will be coinciding with the intrinsic Fermi level EF. Therefore, at T equal to Ti, EFN is simply equal to EFI. That's why you can see that at the temperature I am changing, the Fermi energy level is changing. From where it is changing? Initially, it is at the half of the EC plus ED by EC plus ED, half of the distance, and then as the temperature is increased to TD, it is coinciding with the EFN level, and as the temperature increased to Ti, it is now coinciding with this value. Therefore, this is the variation of the Fermi energy level in N-type materials. Similarly, you can also see in P-type. So in P-type, we have the bands like this. And these bands are now, only difference is that in P-type I have more number of holes. And then the energy levels, which we call it as acceptor energy levels, are close to this, and EFP is this. And these are the two temperatures called the TD and TI. So this is EFI. That means the reference level if it is a intrinsic semiconductor. Now, as the temperature increases, initially in this case, the EF, the Fermi energy level at lower temperature somewhere here, if I take it, is simply is equal to EV. EV is the highest energy level of the conduction band. It is the top of this one. Here I can take, and this is now we call it as donor impurities, acceptor impurities, sorry, and therefore we call it as EA. And initially at T approximately equal to 0K, if I take, this must be equal to EV plus EA by 2, average of these two. It will be at the center somewhere here. And as the temperature increases, the number of breakage of bonds increases and electrons also increases. It moves to this at a Ti. So therefore, at a TD, now the Fermi energy level EF will be exactly equal to EFP. If I still increase the temperature, and if I go to the temperature equal to Ti, then EF is equal to EFI. Therefore, there is a change of Fermi energy level location as the temperature is increased. In P-type also something like this, the acceptor energy levels, it goes like this. So this is how the Fermi energy level varies in P-type and N-type semiconductors with temperature. We'll also look at variation of Fermi energy level with temperature. Okay. But you see that I am now looking at the temperatures 100K, 200K, 300 and 500K. This is the valence band. These are the holes, conduction band. We have some electrons in it, maybe equal in number, an intrinsic semiconductor. Now, in intrinsic semiconductor, EFI we have written it as EFI. I should write this is EFI, and it is exactly at the center if the effective mass of electron is equal to effective mass of hole. If I say these two masses are not equal because they face different potential energies when they are moving in the lattice, sometimes the effective mass of electron is more than the effective mass of hole, or the effective mass of electron is less than effective mass of hole. Therefore, as the temperature increases, I'm taking on this, see the Fermi energy level also changes in case where effective mass of electron is less than the effective mass of hole. If the temperature is changed when effective mass of electron is greater than effective mass of hole, it changes like this. Therefore, this represents the variation of Fermi energy level with effective masses, okay, when temperature is varied. So this gives you the variation of Fermi energy level with temperature for different values of effective masses of electrons and holes. Now I'll see with concentration. Concentration means you may add some impurities to the intrinsic semiconductor to make it extrinsic semiconductor. But how many do you add? I may add maybe, let's say 10 to the power 4 to 5 mother atoms of silicon. I add one impurity only. Or 10 to the power 8, I add one impurity. So as the adding more and more impurities means the concentration of N or P is increasing. as the number of concentrations increasing, the Fermi level also increases. So I am taking here Na or Nd. That means the added donor impurities or added acceptor impurities. This is added acceptor impurities if it is p-type material. This is added number of donor impurities for n-type material. And how many? I am showing 10 to the power 12, 13, 14 to 17 or more. So that many atoms are added. So when I added that many atoms, I will look at the variation of Fermi energy level. This is valence and conduction bands. As you know, we have holes in valence band, electrons in conduction band. This is the intrinsic Fermi level. And the Fermi energy level varies for n-type. See, as the number of donor impurities are increasing, the available electrons in the conduction band increases. And therefore, as the available electrons are increasing with temperature, okay, and with concentration, as the concentration is increasing, the available electrons are increasing, therefore Fermi energy level goes into it. And if I take p-type material, more the number of dopants I'm adding, then holes will be increased, and hence as the increase means that weighted average shifts downwards, and therefore the Fermi energy level for p-type comes to this. You can go for heavy doping like GINA diode or maybe tunnel diode. As you are going for more and more doping levels, then this energy level, instead of like this, it may go into this also band. So we have a Fermi energy level for highly doped having excess charge carriers in the conduction band. If I dope with excess charge carriers, or if their excess charge carriers are generated because of incident light or because of applied voltage, then the Fermi energy level, instead of this one, it go into the valence band or it goes into the conduction band. Such semiconductors which are having heavy doping or heavy excess charge carriers, they are called as degenerate semiconductors. Okay, but here what we were showing, these curves are for non-degenerate semiconductors. Non-degenerate semiconductors in which excess carriers are less or doping is not heavy. If the doping is heavy, the Fermi energy level goes into the conduction band or into the valence band, then we have different Fermi energy levels for conduction band and valence band. Such case semiconductors are called degenerate semiconductors. If the difference between the lowest value, suppose say Fermi energy level is here, if this difference, or if the suppose say Fermi energy level is somewhere here, if this difference is equal or greater than 3 kT, okay, then the semiconductors are non-degenerate. If the difference is Fermi energy level difference is less than 3 kT, they are degenerate semiconductors. So those will be seen in more detail in the higher classes. Now we will look at the how many electrons and how many holes per unit volume per unit energy are there in a conduction band, or how many holes are there in valence band, how many electrons are there in conduction band, we have to calculate it. So that we call it as carrier concentration in intrinsic semiconductor. Extrinsic also we have to do it, and intrinsic semiconductor means that it is the purest form having equal number of electrons and holes. That is, this is also called as intrinsic carrier concentration. Now we would like to calculate and derive a mathematical expression for intrinsic carrier concentration. These how many electrons are there in conduction band, which is called as electron concentration, and how many holes are there in valence band, which is called as hole concentration. If I know these two, I can calculate the total intrinsic concentration, that's charge carrier concentration. To understand it, you have to be very careful and should be very attentive in understanding this. So I have taken a usual one, valence band. here I have represented valence band is having very slightly different energy levels which are closely spaced, that we call it as valence band. And we also can see that there is, okay, we have the top of the valence band is EV, top edge, and now holes are will be there only in this. I have bottom edge of the conduction band as EC, and electrons are there. But see, all the electrons are not same in the energy level. They are slightly different energy levels. Holes also you can show like that. And this is the Fermi energy level. I am taking almost at the center because it is an intrinsic semiconductor. Now I have to calculate how many electrons are there in conduction band, how many holes are there in valence band. Initially we calculate the electrons that are there in conduction band. Remember that electrons will be there for an energy which is equal or greater than EC. That means electrons are there above this. Holes are there below this only. Therefore, if I want to find out the number of electrons in the conduction band, I have to just find how many electrons are there in the small energy gap like this. I call this as E, and I call this as E plus D. And I suppose that the number of electrons in this gap will be, suppose, say Dn, where Dn is a small number of electrons in it. And similarly, I take a small energy gap here, I call it as dP, the number of electrons in the small chosen energy band between E and E. So once I know how many electrons are there in this band and I find Dn, if I integrate Dn from this lowest energy level to highest energy level, that gives you total number of electrons in the conduction band. And if I go for the valence band, same process can be applied. I find how many number of electrons are there in a small energy gap, E plus D, E, and that number I call it as dP. Now I integrate this dP to get the total number of holes P. I integrate this Dn to get total number of electrons. So how to do this mathematical calculation? That calculation is so important, and you have to understand how to take these values, because some of the derivations we have not done, but still we assume that we know some of the expressions. So remember here, electrons will only be there with an energy greater than EC. Holes will be there with an energy less than EV. So therefore, I am now writing Dn, number of electrons, which is called per unit volume, is called electron concentration. We have seen f of E, where f of E is called as probability distribution function, which gives you whether electron is there or not in a chosen energy level. So f of E is electron probability density. G of E is a degeneracy or density of states. If you have sufficient number of energies, then only you can put the electrons. If that level contains electron, f of E is 1. Therefore, I am writing this as Dn is equal to this. But however, it is very simple, because we have defined f of E is nothing but Ni by Gi. And if I write G here, G cancels, I'll get N over the energy range E. Okay, so therefore, I will now apply the simple equation that f of E is N by G into G. G cancels N. It gives you the number of charge carriers in the conduction band for a small gap E and E plus D. And then I have to integrate this. To integrate this, I should know what is the value of f of E and what is the expression for G of E. Here GE/DE is called density of states, that number of available energy states per unit volume per unit energy is called density of states. This is the probability of occupation. F of E is a Fermi function, which we have written as, okay, f of E is equal to 1 by 1 plus e power E minus EF by KT. Now EC is the bottom edge of the conduction band, EV is the top edge of it, and the number of electrons in the conduction band can be calculated by integrating this equation 1. I say this equation number 1 between the EC lowest to highest, that is top of the conduction band. So now I will evaluate N, that is electron concentration. For more description, you just go to this website. And now the energy is F of E GE, because you know that N is equal to integral dN. So that energy level starts, lowest is EC for conduction band, highest I will see soon the top of the CB. Top of the CB means CB is a conduction band. I'll take tip of the conduction band. So thereby I now will evaluate. To evaluate this, we have to know what is GE, which we have not derived, but we assume that the density of states is 2 times 4 pi by m 3 by 2. Actually, I should write me star here. Okay, that will I'll do it soon, because when electron is there in a band, it takes effective mass e power half d. But you see what E have to take it, that is most important. The important value to take E is that not this, the energy is this I'm taking, not the whole energy I should take here, because electrons are there from and above EC, not below this. So this energy is not required for us. Therefore, I will just write here factor 2, because according to Pauli's exclusion principle, 2 electrons can be accommodated in the same energy level. So electrons conduction band will have effective mass me star. I call it as me star. So now I reorder this equation. 2 I am writing as like this. You have 2 power half, here 2 power 1. Therefore, I'll get 2 power 3 by 2. I have this as usual 4 pi by h cube here, and I do have me star here, because m is now replaced by me star and E is the energy. But this energy should be replaced in such a way that this energy will be only for electrons. That's why the energy is minimum is EC. Therefore, E should be replaced by E minus EC. What do you mean by this? This is very simple. To understand this, I have the whole energy here. In this whole energy, okay, you remove this part of it. This is E is the total energy, from which if I might subtract EC, so EC value is this. Then leftover energy is only top of this. Therefore, E minus EC is actually the energy possessed by the electrons in the conduction band. Hence, I replace the E by E minus EC plus 2. And now I just do some mathematical manipulations to substitute the values of GE and also FE. So we have GE value like this. I call this is equation number 1, suppose say, and number 2 will be this equation. Now if I go for this, I will write electrons obey Fermi-Dirac statistics. Thereby I have F of E is equal to 1 by E power E minus EF by KT. And these are the equation 1, 2 and 3. Now I'm substituting. So dN I want to get it. So dN is F of E G of E. So F of E is this. F of E is this. So the entire equation F of E I have written here. And I have to write this equation as G of E. G of E is 1 by this, G of E is this. So I have to integrate this now. If I integrate this, N integral EC to infinity I'm going. Starting we know already that the lower limit is EC. But what is the top level? Why I'm taking infinity? Because we know that a conduction band or a valence band contains too many closely spaced energy levels. Too many are there. And these are so more that their number is very high compared to number of available charge carriers. Therefore, I can take the bottom as EC, and as there are lot number of energy levels are there very closely spaced, I can take the top as almost infinity. That's why I am replacing the integral as EC to infinity, dN. Now I substitute dN here, but this is a constant term. I'm taking out of integration. M may change, but I'm doing integration only with respect to n, therefore that I'm taking out of it. Thereby, I will now get here, this is n, okay, I have substituted everything. And now the upper limit of integration I replaced by infinity energy level. So here I'm taking the same form in the previous slide. This is the integration we have to solve to get the value of n. To solve it, I'm supposing that at room temperature EC minus EV is greater than 4 kT. Therefore, the term in the denominator, this term in the denominator can be simplified like this. I neglect 1 because this value is larger. As this value is large, 1 can be neglected. Once 1 can be neglected, and I will write it as 1 by this term, I am writing something like this. This is 1 I have neglected. If I neglect it, I have only 1 by e power e minus ef by kt. If I take the other side, it becomes minus. So exponential minus e minus ef by t, because I have taken this to top. That's why I have negative sign. And if I just reverse these ones, I can remove this minus sign. That's why I'm writing exponential ef minus e by kt. And this e is now ec. This is ec. Okay, because we have to go up to EC only, and thereby I am writing, okay, so that energy level EC is the starting point, but any energy level electron can take above EC. So this is the values. So I will now write this equation as this as same, whatever is there I am getting here as it is. Integration is like this, and this part is as it is here. And the simplified part for this will be here. That is e power e minus ef. E may be any energy that is changing. So therefore I put e minus ex as a constant because EC is fixed. So if I put that like this, I'll get this EC minus E is x power half. This is x power half I'm getting here. And now I'm changing this, adding and subtracting EC here. I'm adding and subtracting EC. And then in the next step, I am taking the EF is a constant and EC is a constant. And I am leaving E minus EC here and E plus EC, and this I am taking out of it. And it will become EF minus EC. And in this expression I left with e power e minus ec, where e power e minus ec is x. Therefore I am writing minus sign, so I have taken minus sign, that's why it will become ef minus ec, and this I will write it as x by kt. So you should understand that this is x. Okay, in this I have added and subtracted ec, and I have taken minus sign common. After minus sign common, this EF will become plus, which is a constant out of the integration e power, that is. And EC is the bottom of the conduction is also constant. I am taking it out of it. Only one EC, because the other EC is E minus EC, which is x. Therefore, I am substituting x. By KT, it will be there as a whole. Thereby, if I simplify it on integration by using gamma functions, you cannot solve this integration by known simple methods, but you have to use by using a gamma function, which you are going to learn in our higher classes. Therefore, this is a standard integration which I get like this. Now I substitute this in the above equation with this one. If I substitute that, this is will be, I'll get as it is, this 2 will be there, it cancels 2, therefore I'll get it 2. The rest of them is, you see this term how I'm getting, I have 2 pi, here I have, from this if I substitute here, I'll get like this. This term will be there replacing this integral. So thereby I have kt power 3 by 2, okay, and I'm writing kt power 3 by 2 here. me star 2 power 3 by 2, that is me star 3 by 2 is already there. And we have pi 1 by 2 here, and already pi is there here. Therefore pi 3 by 2 I'll get. And here I have h cube. If I go into this h cube, I'm writing as h square to the power 2. Half of goes and I'll get h cube only. Therefore, after rearranging these ones, I will get the entire constant something like this. And therefore, if I just do, okay, this is the constant, and you'll get u. Therefore, n equal to nc into e power f minus kt, where nc is this constant called as effective mass of electrons, and also effective density of states. And this effective density of states is useful in evaluating various parameters. Nc is called effective density of states. In silicon, it may be around 2.8 into 10 to the power something will be there, around 19 some. 10 to the power 19 you can take per centimeter cube. Nc will be there, that many number effective states will be there per centimeter cube. Okay. This is the expression for electrons. Simply also you have to do the expression for the holes also. So holes, I am doing the same expression in the similar manner. Only the change you can do by yourself is that, okay, I have to write now the dp as Ga into 1 minus f of e, because f of e is finding electron, not finding hole. If f of e is the finding electron, then 1 minus f of e is finding hole. That's why I have replaced by this. Therefore, how to find 1 minus f of e? 1 minus f of e is 1 minus this function, Fermi function. And I am taking LCM. If I take LCM, I'll get like this. And if I substitute that and simplify it, assuming this, and I can simplify this and write the f of e as something like this. And now the holes are there below EV only. Therefore, E must be replaced by EV minus E, not E minus EV. If I write EV, this is EV, okay, below. If I from EV, if I subtract all the higher values, these are the higher values E, I'll get negative energy values, which are the values taken by holes. So this should be replaced. And now I have to integrate from top of the valence band to bottom of the valence band, which I can replace it by infinity because there are so many number of energy levels in this. If I do it, I will get the same expression because we have already seen the Ge value, the f of Ge value. Ge value is same as that of electrons, but except Me star is replaced by Mh star. And EC is replaced, E minus EC is replaced by EV minus E. And this function is here. If I simplify that, I will get this P. That means whatever we did the mathematical calculations for electrons, same I have to do here also by supporting and converting into standard integral and do it. But you can do it by yourself. Thereby, I'll get this as NT, ND called as effective density of states. For silicon, it may be around 1.8 into 10 to the power 19 will be there in it. Okay. For silicon, Nc will be more, that will be around 2.8 into 10 to the power 19. Number of states, this is for per centimeter. Okay. So I stop here for the today's class, and we have now seen that the expression for electrons and expression for holes.